We are made of atoms. With each breath, you inhale 10 billion trillion atoms of oxygen, which gives some idea of how small each one is. All of them, together with the carbon atoms in your skin, and indeed everything else on Earth, were cooked in a star some 5 billion years ago. So you were made of stuff that is as old as the planet, 1/3 as old as the universe, though this is the first time that those atoms have been gathered together such that they think that they are you. Particle physics is the subject that has shown how matter is built and which is beginning to explain where it all came from. It has revealed the existence of a ubiquitous essence known as the Higgs field, which gives mass to matter's fundamental particles. In huge accelerators, several miles in length, we can speed pieces of atoms, particles such as electrons and protons, or even exotic pieces of antimatter, and smash them into one another. In so doing, we're creating, for a brief moment, in a small region of space, an intense concentration of energy which replicates the nature of the universe as it was within a split second of the original Big Bang. Thus, we're learning about our origins. Discovering the nature of the atom 100 years ago was relatively simple. Atoms are ubiquitous in matter all around, and teasing out their secrets could be done with apparatus on a tabletop. Investigating how matter emerged from creation is another challenge entirely. There is no Big Bang apparatus for purchase in the scientific catalogues. The basic pieces that create the beams of particles, speed them to within an iota of the speed of light, smash them together, and then record the results for analysis, all have to be made by teams of specialists. That we can do so is the culmination of a century of discovery and technological progress. It is a big and expensive endeavour, but it is the only way that we know to answer such profound questions. In the course of doing so, unexpected tools and inventions have been made. Antimatter and sophisticated particle detectors are now used in medical imaging. Data acquisition systems designed at CERN, the European Council for Nuclear Research, led to the invention of the World Wide Web. These are but some of the spin-offs from high-energy particle physics. The applications of the technology and discoveries made in high-energy physics are legion, but it is not with this technological aim that the subject is pursued. The drive is curiosity, the desire to know what we're made of, where it came from, and why the laws of the universe are so finely balanced that we have evolved. In this very short introduction, I hope to give you a sense of what we have found and some of the major questions that are now confronting us. I'm indebted to Latham Menon at Oxford University Press for encouraging me to produce this new edition, and to Alphonse Weber for his advice on some aspects of experimental particle physics.